Howdy, and welcome to Amine 315, lecture number 25. Okay, so we've got a lot to cover today, so we're going to go ahead and get started. And greetings from London, by the way. But just to provide some reminders to begin, first of all, homework number 10 is due on Tuesday, November 19th at 3 o'clock in the afternoon, and you can submit that to my office, 321 Mechanical Engineering Office Building. Just put your homework in the wire basket outside my office. Also, homework number 11 is assigned and is due not next Tuesday, but the following Tuesday. So Tuesday, December 3rd at the start of class. So this is the Tuesday following Thanksgiving. Thanksgiving is, of course, next Thursday. Also, there's no class on Thursday, November 21st. I'll be posting a lecture, online video lecture for that, so make sure that you watch that instead. And for both today's lecture as well as the lecture that will be posted for Thursday, your participation assessment on Tuesday, November 26th, the next time that we all get together, will be graded. And it's going to cover the lecture content from today's lecture, lecture number 25, and from lecture number 26. Project report is due on Tuesday, December 3rd, which is the last day of class, so make sure that you have that wrapped up and completed. And then finally, the course evaluation in this class is going to be done online with the PICA evaluation system. So to access that, you go to pica.tamu.edu, and you want to make sure that you do this before the last day of class so that you can evaluate the course. I won't see the results until after the final grades are submitted, so you're able to give your honest feedback on how the class can be improved. Please be sure to participate. I very much value students' feedback, and I always try to take your suggestions into consideration, and so your feedback is very much appreciated. Okay, so on to the lecture material. So what are we talking about today? Well, if you remember where we were last week and in the few weeks leading up to today, we basically started talking about heat engines and heat pumps and refrigerators, and we started to combine all of these different components that we've talked about all semester long, things like boilers and condensers and turbines and pumps. And we combined them together and said that these components allow us to make up what we call heat engine cycles, where a heat engine takes thermal energy and converts it to work energy, or heat pump cycles, which transfers thermal energy from low temperature to high temperature by using work energy input. We then further analyzed the heat engine and heat pump cycles, and we asked ourselves a few questions such as, what is the most efficient heat engine cycle, or what is the heat pump cycle that has the highest coefficient of performance? And after much discussion, we talked about things like the Kelvin-Planck statement and the Clausius statement. We came up with what is called the Carnot device, or the Carnot cycle, where the Carnot cycle is the perfectly reversible cycle. It's totally reversible. It's the ideal cycle, which is to say that if a heat engine is operating on the Carnot cycle, it's producing a certain amount of work, where if you put that work into a reversible heat pump, a heat pump working on the Carnot cycle, then you would be able to return the thermal energy back to the high temperature reservoir in a total reversible cycle. We also talked about what the various processes that make up the Carnot cycle are, and we realize that those four processes don't do a very reasonable job predicting anything that we could implement in practice. In other words, real systems require a gradient, a temperature gradient, in order to do heat transfer. Whereas in the Carnot cycle, that heat transfer process, because it has to be ideal, has to be reversible, that heat transfer process doesn't occur through a temperature gradient. The temperature of the system is the same as the temperature of the surroundings. But that's not how a real system works. A steam power plant, for example, uses a very high temperature gradient so that it can transfer thermal energy into the water. And so, given these practical constraints of the Carnot cycle processes, right? So, for example, we've got this constant temperature heat transfer process in the Carnot cycle. Its only purpose, really, is to serve as a theoretical construction for the second law. That's really what the Carnot cycle does for us. It doesn't really give us an opportunity to analyze a real device. It just tells us what the maximum possible efficiency of a real device could be. In spite of this, though, we would like to be able to model real systems. That's what we do as engineers. As engineers, we are constantly constructing models in order to either analyze or design or build something up in a more appropriate fashion. So we would like to be able to model these real systems. We'd like to be able to model a real steam power plant or a real heat pump or a refrigerator. And that's what cycle analysis does for us. The idea of cycle analysis is to construct ideal cycles of practical devices, such as heat engines and heat pumps. So how is this different than the Carnot cycle? Well, the cycles that we will talk about here are only ideal in the sense that they're internally reversible. The Carnot cycle was totally reversible. It's reversible both internally and externally. Therefore, the processes of the various cycles that we'll discuss are going to be specific for a practical application or for a practical device. There's not going to be one single cycle that works for all of these devices that we talk about. Each device, whether it be a steam power plant or a reciprocating piston engine or a rotating jet engine, rotating turbo machinery engine, for example, or a refrigerator or an air conditioning system, they all have unique processes that they typically operate by. And cycle analysis allows us to define the processes of these cycles and then conduct engineering thermodynamic analysis on them. Okay, so we're going to talk about several cycles in the next basically until the end of the semester. This is really going to conclude the semester for us. And so I've got a little org chart, if you will, of cycle analysis, right? So you've got president and CEO up here at the top, cycle analysis. And we can break cycle analysis, we can divide it into two parts. There are cycles that are specific to heat engine applications, and there are cycles that are specific to heat pump applications. Now, in the heat engine applications area, we can break that down into two categories as well. There are cycles that are what we call vapor power cycles, and we'll define that in just a little bit. And there are cycles that are what are called air standard power cycles. And we'll start talking about the air standard power cycles maybe a little bit on Thursday, but for sure next Tuesday. So within the vapor power cycles is where we have the infamous Rankine cycle. We've talked about the Rankine cycle a few times this semester, even if we really haven't called it the Rankine cycle. The Rankine cycle is the simple steam power plant cycle. So most steam power plants around the world are operating on what we call the Rankine cycle. Now there's lots of variations to the Rankine cycle, and your textbook does a really good job at going into all those variations, and I don't expect you to have to necessarily memorize all those, but you may want to read it for interest's sake. But one of the variations is what we call the reheat cycle. So today we're going to talk about the Rankine cycle, and then in lecture number 26 we'll talk about the reheat cycle. In the category of air standard power cycles, this is where our our reciprocating piston cycles exist. So the Otto cycle and the diesel cycle are two air standard power cycles that we'll start talking about next Tuesday. Then in the non-heat engine category, the heat pump category, we also have several different cycles that we could talk about, but our textbook really only talks about one, and that is the vapor refrigeration cycle. And so we'll briefly mention the vapor refrigeration cycle on the last day of class on Tuesday, December 3rd. So the numbers that I have listed above each of these cycles is basically the order of discussion. So we're first going to talk about vapor power cycles, we're then going to talk about air standard power cycles, and then finally we'll talk about heat pump cycles. Okay, so vapor power cycles. What are vapor power cycles? Well, the vapor power cycles are used to model heat engines, right? It's a heat engine cycle. And the reason why they're called vapor power cycles is because they rely on the substance vaporizing and condensing through the process or through the cycle. So water is very commonly used in a vapor power cycle. It doesn't have to be used, but water is typically what is used in a vapor power cycle. For example, power plants around the world all have water as their working substance, undergoing the simple steam power plant cycle. So yeah, the steam power plant is an example of a cycle that operates as a vapor power cycle. Now, a specific type of vapor power cycle, which is really the most common type of vapor power cycle, is the Rankine cycle. And there's lots of different variations to the Rankine cycle, but the basic Rankine cycle is composed of 4 open processes. So notice I put open here. That's important to note because that's going to dictate what first law equation we write down when we go through and do the cycle analysis. So when I say that each process is open, that just means that the process is open. It doesn't necessarily mean that the cycle is open. In the case of a Rankine cycle, the cycle is in fact closed, or at least mostly they're closed. But a heat engine cycle doesn't have to be closed. A heat engine cycle could in fact be open. And that's actually the primary reason why an internal combustion engine does not abide to the information that we get from the Carnot cycle. An IC engine doesn't precisely operate on a thermodynamic cycle. And it's not because it's open. It just has to do with the fact that you don't return your system to its initial state, right? You start with reactants of fuel and oxidizer, fuel and air, and you end with products of combustion such as CO2 and water and other products of combustion. But that water and CO2, the products of combustion, they don't recombine to make fuel, which was what your initial state was. So because your system doesn't return to that initial state, an internal combustion engine does not operate on a cycle, a thermodynamic cycle that is. It operates on a mechanical cycle, doesn't operate on a thermodynamic cycle, and therefore an internal combustion engine is not rigidly considered a heat engine. A steam power plant, however, does operate on a cycle. The water returns back to its initial state, and they typically operate as closed cycles, which means that the system is never open to the atmosphere, basically. It always remains closed. Okay, so what are the 4 processes that make up the vapor power cycle? There are 4 for the simple basic Rankine cycle, and they are as follows. The first process, process 1 to 2, is a reversible and adiabatic pressure increase. So this is what we call our pump process. Process 2 to 3 is an isobaric, and that word isobaric means constant pressure, heat addition process. And so this would be what we would call our boiler process. Process 3 to 4 is a reversible and adiabatic pressure decrease. This is our turbine process. And process 4 to 1 is an isobaric, again, constant pressure, heat rejection process. And so this is our condenser process. So we can draw what this looks like. So we have our heat engine, right, our 4 processes. These 4 processes basically compose our heat engine cycle, and they operate between a high temperature reservoir and a low temperature reservoir. So by accepting thermal energy from the high temperature reservoir in the boiler, we make steam, and this steam then is expanded through the turbine and produces turbine work, and a fraction of that turbine work goes into delivering work into the pump, since that's our pressure increase process. And then the balance that doesn't get transferred into the pump is leaves the heat engine system as net power, this W dot net. After leaving the turbine, the steam is then cooled, where this Q dot L, this necessary heat rejection, takes place, and Q dot L is sent to the low temperature reservoir T sub L. Excuse me. And then, of course, we have the pump process that increases the pressure in the system and provides some mass flow rate for the cycle to operate in a cyclic fashion as it does. We can also draw the four processes. Just to reiterate, this is process 1 to 2, our pump process. This is process 2 to 3, our boiler process. Process 3 to 4 is our turbine process. And process 4 to 1 is our condenser process. So we can go ahead and draw the four processes on a TS diagram. And of course, we want to make sure that we include the saturation dome because the Rankine cycle is a vaporizing cycle. And so our substance is going to be phase changing. And what I've drawn on this TS diagram is you'll notice I've drawn TH and I've drawn TL. So the temperature at the end of the heat addition process, at the end of the boiler process, is the highest temperature in the cycle. But of course, that high temperature in the cycle is still less than the high temperature reservoir. This is now where we can build in that gradient to ensure that we have heat transfer between the high temperature reservoir and the cycle. Likewise, we have our low temperature reservoir. This is where our cooling medium is at, but that's lower than the low temperature in the cycle itself. Again, we need to have that gradient present so that we can reject the thermal energy from the cycle into the low temperature reservoir. So state 1 is before going into the pump process. And one of the typical assumptions that we make about the Rankine cycle, aside from the fact that usually when we say Rankine cycle, it almost always means that water is the substance of the cycle. You can basically assume that when you see Rankine, water is the substance, and you would be told otherwise if you're not analyzing water in a Rankine cycle fashion. The other typical assumption is that state 1, which is the state after the condenser process, after the heat rejection process, and before the pump process, is a saturated liquid. So we start here at state 1 at our saturated liquid state. We then undergo our constant entropy, our reversible and adiabatic pressure increase from pressure at P1 to pressure at P2. We then undergo our constant pressure heat addition process. So this curve that you see here is following the line of constant pressure, adding thermal energy from state 2 up to state 3. We then have process 3 to 4, which is our turbine process. That's our reversible and adiabatic pressure decrease, the expansion process. And because it's reversible and adiabatic, or isentropic, the entropy at state 4 is the same as the entropy at state 3. And then finally, the final process in the cycle is our constant pressure heat rejection process from state 4 to state 1. And that's what we have shown here as we follow the line of constant pressure. That corresponds to the saturation pressure when the system is at a temperature of T1. Okay, so we can go ahead and do a process-by-process analysis to understand how we would find things such as the work transfer and the heat transfer. And ultimately what we want to find from a Rankine cycle analysis is what the net work of the cycle is and what the efficiency of the cycle is. So for our first process, we have process 1 to 2. This is our reversible and adiabatic pump process. And when we do a first law analysis, we see that our energy in, that is Q plus H1, of course we're neglecting kinetic and potential energy there, and that's written on a mass-specific basis, is equal to our energy out, which is work plus enthalpy at state 2. It's an adiabatic process, so Q is equal to 0. And so we're left with the work is equal to H1 minus H2. Now, typically H1, state 1 is fixed. So if we wanted to calculate the work transfer, we have to be able to fix state 2. Now, usually the pressure, the maximum pressure in the cycle is known, or somehow you're able to determine the maximum pressure in the cycle. So you usually know one independent property at state 2. But we have to figure out what the second independent property at state 2 is. So our natural course of action has been to look at the second law. So when we do a second law analysis of process 1 to 2, we see that the entropy at state 2 is equal to our heat transfer entropy that's added by thermal energy, plus our entropy at state 1, plus the entropy generation. Of course, it's a reversible process, so our entropy generation term is equal to 0. And it's an adiabatic process, so our heat transfer is equal to 0. So as we expect, when we see the words reversible and adiabatic, that means that it's an isentropic process, so S1 is equal to S2. Now, this is where we have to take a small departure from how we would normally do things and introduce a new concept here. This would all be well and good, where our second law tells us a second known property at state 2. It tells us that the entropy at state 2 is the same as the entropy at state 1. And if we know our pressure at state 2, then you would think that we have two independent properties, P2 and S2, at state 2. The problem that we run into when we use our booklet of tables is that it's really hard in the liquid region to take this information and pressure and be able to determine a second or a third property such as enthalpy or temperature, for example. So we need to do something else in order to find H2 here in our work equation. And the something else that we can rely on is the fact that we're pumping a liquid. So because we are pumping a liquid, we can employ the incompressibility approximation. You remember the incompressibility approximation is when we say that the substance is incompressible, that is, its volume doesn't change substantially as its pressure changes. And when we impose incompressibility, that means that the specific volume stays constant. Well, how does that help us? Okay, well, what we need to do is we need to actually develop an expression of work transfer that we haven't talked about yet, at least not directly, but it's pretty important to know. To do this, what I'm going to ask us to do is to recall one of our TDS expressions. So do you remember a few weeks ago in lecture, we basically had a lecture where we derived a bunch of equations for ideal gases, and we started with what we call the two TDS equations. Well, one of the TDS equations is as we have written here. TDS is equal to dH minus V dP. Okay, well, how does that help us? Well, for our process, it's reversible and adiabatic, so ds is equal to 0. Since the left-hand side is equal to 0, it means that dH minus V dP is equal to 0. Or dH, the change in enthalpy, the differential change in enthalpy, is equal to the specific volume times the change in pressure. We also noted from our process that the work transfer is equal to H1 minus H2. Now, if I write this on a differential basis, what that is saying is the change in work, the delta W, is equal to negative dH, right? This is H1 minus H2, not H2 minus H1, which would be a positive dH. So I can equate the fact that I have this expression here where dH is equal to VdP and this expression here where delta W is equal to negative dH. I can equate those two and I get the following result. Delta W is equal to negative V dP. So even though we analyze this for our specific process of an incompressible substance and reversible and adiabatic process, it's actually a general result. And this equation that I have boxed here, this delta W equal to negative V dP, is something which we call work or shaft work. It's a specific type of work transfer called shaft work. And just to be very rigorous here, this shaft work should not be confused with boundary work, which looks very, very similar, and we've talked about boundary work a lot in the context of closed system analysis with piston-cylinder arrangements, but they're two very different expressions, as I have summarized here in the notes. The shaft work is negative V dP. Boundary work, however, is P dV. No minus sign, and the terms being differentiated or not being differentiated are different. So this expression here for shaft work equal to negative V dP, this is what we call the shaft work equation, and this is commonly associated with open system shaft work transfer. So if you have a turbine, for example, it's transferring work out that's governed by this equation. Likewise, if we have boundary work, which is PdV, this is the boundary work equation that is commonly associated with closed system boundary work transfer. So note the difference and don't confuse them. But if we return now to our analysis of the Rankine cycle, since our pump process is pressurizing a liquid, which we can treat as incompressible, that means that the specific volume of the water stays roughly constant as it undergoes the pump process. So we got from our first law result that delta W is equal to the integral of 1 to 2 of dH, and this is equal to the integral from 1 to 2 of negative v dp. Well, the integral of dH from 1 to 2 is just h2 minus h1. And because our substance is incompressible, we can pull this specific volume out of the sign of integration and get that this is negative v times the integral from 1 to 2 of dp. And this integral, the integral from 1 to 2 of dp, is also easy to analyze. So what we get by combining all of this is that our change in enthalpy between state 2 and state 1 is equal to negative v, the specific volume of the liquid water, times the change in pressure. So if we take a look at this, this is how we will typically find our enthalpy at state 2. So state 1 is typically known. We know that, we can make the common assumption that state 1 is a saturated liquid at the low temperature in the cycle. And pressure at state 2 is often given. So we can look up H1, we can look up V, we can just take this to be V1. P1 is usually given, and P2 is usually given. So we can use this expression to find H2. That then allows us, if we go back up to our work transfer equation, that then allows us to solve for the work transfer for process 1 to 2. But, as we'll soon learn, that H2 is also used later on in process 2 to 3. So let's take a look at process 2 to 3. So in the case of process 2 to 3, we have a constant pressure boiler or heat addition process. And really the only thing that we'll be able to write of substance for this process is our first law equation, where we can say that Q2 to 3, the heat transfer, plus our enthalpy at state 2 is equal to the work transfer plus our enthalpy at state 3. Now this is a boiler process, and remember that boilers are not designed to transfer work. They're just designed to transfer thermal energy. So the work transfer for process 2 to 3 is equal to 0. And we get that Q2 to 3 is equal to H3 minus H2. So H3, usually enough information is known about state 3 that we can look up H3. And we found H2 in our analysis of process 1 to 2, which we had just described. The other important item to note is that this Q2 to 3, remember, is the same as QH. QH is what's being added from the high temperature reservoir, and since that gets added to the boiler, process 2 to 3, these statements are all equivalent. The next process to analyze is process 3 to 4. And process 3 to 4 is our reversible and adiabatic turbine process. So again, we can go ahead and write the first law for process 3 to 4. And we get that Q3 to 4 plus H3 is equal to work 3 to 4 plus H4. So it's, of course, an adiabatic process. So Q3 to 4 is equal to 0. And we get that work 3 to 4 is equal to H3 minus H4. Now again, we may have to fix either state 3 or state 4, depending on what information is available to us. So we may need to rely on the second law to help us fix either state 3 or state 4. So of course the second law equation for this process is that S4 is equal to Q divided by temperature plus the entropy at state 3 plus the entropy generation. It's a reversible process, so Sgen is equal to 0, and it's an adiabatic process, so our heat transfer term is equal to 0. So of course we get that entropy at state 4 is equal to entropy at state 3 for this reversible and adiabatic process. Now, one item that I want to point out here is that this statement is true. We can definitely say that the shaft work, delta W, is equal to negative integral of VdP. But what's also important to note is that this equation doesn't really help us. And the reason why it doesn't help us is because V is not constant through the process. And we usually don't know how V varies with pressure. And so this form of the shaft work equation for this particular process is not too terribly helpful. Okay, we can then go on to process 4-1, which is our constant pressure condenser process, our heat rejection process. And so our first law tells us that Q4-1 plus H4, which is equal to work 4-1 plus H1. And because it's a condenser, it's designed to transfer thermal energy. It's not designed to transfer work energy, for example. We get that Q4-1 is equal to H1 minus H4. And just like above, where Q2-3 was equal to QH, we can also say that Q4-1 is equal to the negative of QL. It's important to remember that that's equal to the negative of QL, because all semester long, we've been writing the first law equation for our heat engine with taking into account the fact that QL was leaving the system. So it's important to make sure that you retain that minus sign when equating Q4-1 to QL. Okay, so now that we've gone through and analyzed each of the processes, we would then basically do what we're after by doing the cycle analysis. And that is to calculate the net work, right? We're really interested in knowing what the net work from the cycle is. And I'll just remind you that, we are still talking about a heat engine cycle. So all of the information that we talked about earlier when talking about heat engines, such as net work is equal to QH minus QL, still applies. This is all still true. And we're also interested in knowing the efficiency of the cycle. And so I'll just remind you that the efficiency of the cycle is the net work divided by the high temperature heat input, or QH. And since net work is equal to QH minus QL, we can substitute that into the efficiency equation and say that efficiency is equal to 1 minus QL over QH. So if all you're really interested in knowing is the efficiency of the cycle, you only have to calculate two terms, QL and QH. Now, it's also important to note that one thing that we haven't done here is we haven't set this efficiency equal to the ratio of temperatures. In other words, we're not saying that the efficiency of the Rankine cycle is equal to 1 minus TL over TH. The reason for that is that relationship, 1 minus TL over TH for the efficiency of the heat engine, is only applicable for Carnot cycles. This is not a Carnot cycle, this is the Rankine cycle. And so making that connection would be incorrect to do. Okay, so I have an example for you, and this basically just sort of pulls together all of the information that we've talked about the Rankine cycle so far. So we have in this example a simple steam power plant, and it's operating on a Rankine cycle with saturated vapor at 3 megapascals leaving the boiler. Okay, so that piece of information that was just given to us there is in fact telling us our state 3 information. We're also told that the turbine exhausts to the condenser, and the condenser is operating at 10 kilopascals, the low pressure side of the cycle. We're asked to find the specific work transfer and the specific heat transfer in each component, and to calculate the cycle efficiency. Okay, so to do this, I have it starting on the next page here. There we go. So the first thing that I do is I draw the simple steam power plant cycle. So I have it drawn the same way that we talked about in the lecture notes, where we have process 1 to 2 as our pump process, process 2 to 3 as our boiler process, 3 to 4 is our turbine process, and then 4 to 1 is our condenser process. And I also like to draw this on TS diagrams. So we have our TS diagram over here. Of course, we've got our saturation dome. It's important to remember to include the saturation dome. And we start state 1 here on the saturated liquid line. Remember, that's one of the typical assumptions that we make with the Rankine cycle, is that the state after the condenser but before the pump is on the saturated liquid line. So that's our state 1. We then have process 1 to 2, which is our reversible and adiabatic pump process. So it's constant entropy. So state 2 is directly above state 1, but at a higher pressure. We then have process 2 to 3, which is our constant pressure heat addition process. Now, state 3, we're told, is a saturated vapor at 3 megapascals. And so I have state 3 drawn right here on the saturated vapor line. We then have process 3 to 4, which is our reversible and adiabatic pressure decrease process, or our turbine process. And so because it's reversible and adiabatic, or isentropic, state 4 is directly beneath state 3. And then to close our cycle, we have process 4 to 1. So this is our returns process. And that is, of course, a constant pressure heat rejection process going in the direction toward number 1. I also like to write down state information. So we know, for example, that because we're told that the low pressure in the cycle is 10 kPa, we know that that's the pressure at state 1. State 1 is at the low pressure in the cycle, as well as state 4, since process 4 to 1 is a constant pressure process. At present, we don't really know anything about state 2 except the fact that we know pressure at state 2 is the same as pressure at state 3 because process 2 to 3 is a constant pressure process. But we don't know anything else about state 2 just yet. We were given lots of information about state 3. We were told that the pressure is equal to 3,000 kPa and that the quality at state 3 is equal to 1. Now you may be wondering, well, I don't remember seeing quality being equal to 1 in the problem statement. And that is true. We weren't explicitly told that quality at state 3 is equal to 1, but we were told that it's a saturated vapor after the boiler process. And so since it's a saturated vapor, state 3 is right on that saturated vapor line, and therefore the quality at state 3 is equal to 1. We then have process 3 to 4, which is our constant pressure decrease, not constant pressure, our reversible and adiabatic pressure decrease. And so our entropy at state 4 is the same as the entropy at state 3. And then finally, state 4, because it's a constant pressure process between state 4 and state 1, we know the pressure at state 4 is equal to 10 kPa. So we're, of course, wanting to find the work transfer, the specific work transfer, as well as the specific heat transfer in all of the processes. So doing a process-by-process analysis, that's typically what we do when we do a cycle analysis. We start with process 1 to 2, which is our isentropic pump process. And since it's isentropic, it's reversible and adiabatic, our Q is equal to 0. And our first law equation tells us that work from 1 to 2 is equal to H1 minus H2. Since, as we talked about in the analysis of the development of the Rankine cycle, only for process 1 to 2, because the specific volume of the water doesn't change during that pump process, we can say that this H1 minus H2 is equal to negative V P2 minus P1. So also, since process 2 to 3 is a constant pressure process, we know that pressure at state 2 is equal to pressure at state 3. And likewise, since process 1 to 4 is a constant pressure process, we know that pressure at state 4 is the same as the pressure at state 1. Okay, so we can find out H2 easy enough because we can use our equation up here, our work equation. And so we get that we have the pump that's pressurizing a liquid. And at state 1, we have state 1 being a saturated liquid. So its specific volume is equal to the saturated liquid specific volume at a pressure of 10 kilopascals. So when we go to table A4 to look that up, we see that the specific volume at this pressure as a saturated liquid is 0.001010 cubic meter per kilogram. Since P2 is equal to P3, which is equal to 3,000 kPa, and P1 is equal to 10 kPa, we can calculate the work transfer for process 1 to 2, which is equal to negative 3.02 kilojoules per kilogram. Also, since work 1 to 2 is equal to H1 minus H2, we can say that our enthalpy at state 2 is equal to our enthalpy at state 1 minus our work transfer, bearing in mind that this work transfer is actually a negative number. So again, we need to know what H1 is, so we go to table A4 and we look up the saturated liquid enthalpy at the pressure of P1, 10 kPa, and we see that the enthalpy at that condition is 191.81 kilojoules per kilogram. So knowing this information, we can then plug that into our equation for H2 and get that the enthalpy at state 2 is equal to 194.83 kilojoules per kilogram. Moving on to process 2 to 3, this was our constant pressure heat addition process. So our heat transfer is equal to H3 minus H2. H2 we already know, we determined that from our process 1 to 2 analysis. And H3 we also know because we know that state 3 is saturated vapor at a pressure of 3,000 kPa. So the saturated liquid enthalpy at state 3 is equal to the saturated vapor enthalpy at a pressure of 3,000 kPa. So we go to table A5 to look this guy up, and we see that the enthalpy at that state is equal to 2,803 kilojoules per kilogram. Plugging all of this back into our first law equation, we get that Q2 to 3 is equal to H3 minus H2. And plugging in now our known values, we see that Q2 to 3 is equal to 2,608 kilojoules per kilogram. We can then move on to our process 3 to 4, which is our isentropic expansion process. So again, it's reversible and adiabatic, so Q3 to 4 will equal 0 for this turbine process. And work 3 to 4 is, from our first law analysis, equal to H3 minus H4. Here we do have to use our second law equation to help us to fix our unknown state. So in this case, the unknown state is the entropy at state 4. Based on second law analysis, we see that the entropy at state 4 is equal to the entropy at state 3, which when we go to look the entropy value at state 3 up in the table, we can go to table A5, and the entropy at state 3 is equal to the saturated vapor enthalpy at a temperature of T3. So now when I look at this entropy value and where I find it in my tables, I actually find it in the saturated tables. So, and if we look at our TS diagram, this makes sense, right? We have state 3 that's right here, right on the saturated liquid line, and because of the curvature of the TS dome, state 4 is going to be underneath state 3 where it has quality, right? Where it's a two-phase mixture. So in order for us to determine the enthalpy at state 4 so that we can calculate work 3 to 4, we have to know what that quality value is. And so we go ahead and say that our enthalpy at state 4 is equal to the saturated liquid enthalpy at a pressure of 10 kPa plus the quality times the latent vaporization of the latent energy of vaporization, HFG, the difference between Hg and Hf. So knowing our entropy at state 4, we can use our quality equation, where quality is equal to S4 minus the saturated liquid entropy at a pressure of 10 kPa divided by the entropy of vaporization, SFG, at a pressure of 10 kPa. That then gives us our quality, and so our quality at state 4 is equal to this 0.738. Now that we know what the quality is, we can then use it in the other direction to determine the enthalpy at state 4. So in this case now, enthalpy at state 4 is equal to the saturated liquid enthalpy at a pressure of P4 plus the quality times the enthalpy of vaporization at a pressure of 10 kPa. So when we plug all of this in, we get that the enthalpy at state 4 is equal to 1,957.2 kilojoules per kilogram. Now with that information, we can now calculate our work transfer for process 3 to 4. So that was equal to H3 minus H4. We now know both of those parameters. And so we get that the work transfer from 3 to 4 is equal to 846 kilojoules per kilogram. The final process is process 4 to 1, and this is our constant pressure heat rejection process. So in the case of our first law analysis for this process, we get that the enthalpy at state 1 minus the enthalpy at state 4 is equal to Q4 to 1, our heat transfer for that process. Whoops, excuse me. So we know H1 and we know H4, so we can just plug these quantities into our equation and get that our heat transfer Q4 to 1 is negative 1,765 65 kilojoules per kilogram. So the final thing that we're asked to calculate is the efficiency of the cycle. And so, of course, the efficiency of the cycle is defined as the net work divided by the high temperature heat input, or QH. And you could either calculate the net work one of two ways. You can either sum work 1 to 2 with work 3 to 4, or you can recognize that Q2 to 3 and Q2 to 4 necessarily must equal the work transfer, right? Based on the fundamental statement of the first law, conservation of energy, the cyclic integral of work transfer is equal to the cyclic integral of heat transfer. This W net basically represents the cyclic integral of work transfer, and so this numerator is also equal to Q2 to 3 plus Q4 to 1. So it's just easier, since I didn't directly calculate the net work, it's just easier to plug these two numbers into the efficiency equation, and we get the following, that Q2 to 3 is equal to 2608, Q4 to 1 is equal to 1765, and Q2 to 3 is equal to 2608, all kilojoules per kilogram. And when we plug those numbers in, we get that the efficiency of the cycle is equal to 32%. Okay, so that's actually all that I had for today's lecture. We were able to go through it fairly quickly because this cycle analysis, again, is just reintroducing concepts that we've already gone over. In spite of that, if you have any questions about anything, please post them to the discussion board or feel free to send me an email. Otherwise, I'll look forward to generating lecture number 26, and I hope that you all have a good day. Bye-bye.